Oh, hi. Tonight I'm going to show you how to do the calculation between the amplitude of the sine wave and its energy. In the ham radio RF frequency, you can think of frequency is the ham radio signal is composed of a group of the sine wave with different frequencies, and they are in the same band and shoot out. The pure CW, the Morse code, is using one sine wave to shoot out. For example, this is the 52 6-meter band, 52 megahertz. If you send this tone out of your radio, you can hear the very steady tone. It's a so now let's do a calculation on how to get the energy out this sine wave. Okay, I'm going to do lots of math. So the pure sine wave tone is like this one, and this is one cycle, say t seconds. So it's repeating itself, and this is the peak value called Vp. So the tone is like that. And how to calculate the energy of this one? We know in the DC this is the AC world, and in the DC world, the the amplitude V is steady, and it's called V, and the power equals V square over resistance. But in the AC, we cannot use the DC calculation. We basically to cut into small pieces, and we calculate each piece, and this is basically the integral. So let's represent this tone in a mathematical formula. Say the tone voltage in volts equals to Vp sine 2 pi over t and t. Okay, this is the representation of this tone. You can see if the t is pi, it's 0. If t is pi over 2, this is Vp. So this is representation. If we cut into small pieces, then we can calculate the energy. So the power equals the total energy of one cycle, which is 0 of t Vt square dt divided by the duration. So this is the power. And we can go further. The resistance here. So it's a resistance Vp square sine 2 pi t square dt, and we can get those constants out. So the constants is Vp square tr and we know that sine square is equal to 1 over equal to 1 minus cosine, double this one and divide by. So I do it. Vptr. So this is sine square equal to half of 1 minus cosine and double the contents, which is 4 pi t. So this is equals to tr times 2 Vp square dt minus cosine 4. Okay, we got this one. And basically this is a t integral minus cosine is the sine, so it's a sine 4 pi t over t, and the parameter will flip 4 pi over t, then 0t. And you can see put t here, well, it's 0, sine of 4 pi is 0, 0 here, sine of 0 is 0. So this is out. So this will become t. So t and t cancel out. So it becomes Vp squared 2. So we know the power. We find the power. The power equals to 2Vp squared. Vp is the peak amplitude. If we use okay, this is R here. If we use equivalent DC voltage of the same resistance, that DC voltage is called RMS. So it's the same as V RMS square over 2. So we can see RMS equals to square root of OVP square equals to Vp equals to 0.707 Vp. So now we can see that normally people say, okay, I use the RMS. So RMS is 0.707 of the peak value Vp. It's easy to remember. So, but the actual power is this one. Okay, let's continue. So now we know the power equals to Vp square over 2R. I is the resistance. In our world, the unit of P is watts, and the Vp unit of Vp is watts. Normally we don't do that. The signal is so low, this watts and watts is too high, so we use milliwatts. So 1 watt equals to 1000 milliwatts, and 1 watt equals to 1000 milliwatts. So that's using watts milliwatts to convert this frequency, equation. So this power in the milliwatts divided 1000 equals to power peak voltage over the milliwatts 2R. So now we had a frequency, say PM equals to 2 times 1000 times R Vp in milliwatts. Okay, and this is the this square. So we got this value. So many times it's very easy to use log based 10 base log to represent this one, and this is base is milliwatts. But if we use log, which is P log, if 10 base, I just use LG. In the milliwatts, we define this one as 10 times log. This is 10 based. PM, so equals to 10 log. Yeah, I dropped the 10 base 10, so I just use LG instead of LOG. This 2 times 1000 R Vp m square. This is equals to what? 20 log Vpm minus this is 3, so it's 30, and minus 2R left, 2R, so it's 10 log 2 times R. Okay, we got this formula. Normally in the radio, the resistance, we use 50 ohm. So this oh, sorry, this is not called log m. it's there's a word called dBm. It's in dB scale, so it's p dBm equals to 20 log VPM minus 30, and this is 50, so it's 100. Log 100 is 2, so 2 times 10 is 20, so 20. So basically, effectively, it's this minus 50. Okay, so now we get a dBm, the relation between dBm and the peak voltage. dBm is the is milliwatts, and VPM is in the peak value in the milliwatts. So we got this this equation. Now let's put it into some real use. Let's write it again. P in dBm equals to 20 times log Vp in milliwatts minus, okay, we're talking about this is a 50 ohm resistance. In the radio, in the icon radio specs, it says that S9 in the S meter, S9 basically is a full bar. S9 also means that 73 dBm power, and now we want to see what's the voltage. Okay, so we put this one in, like 73 equals 20 log VPM minus 20, so it's VPM equal 10 based, this is over 20, like 73 plus 50, so effectively it's 10 to 20 minus 23, 10 to minus 1.15, and we got value. This is 0.07079 milliwatts. Also, my signal generator does not use this peak value. It used the peak to peak. It's P to P, so it's double the peak value. It's from here all the way to here. So equivalent say V P to P in milliwatts equals to double this value is 0.14158 milliwatts. So basically, it's telling me that if I shoot P2P value signal with P2P amplitude at 0.1415 milliwatts, I can receive S9 signal. This is a very, very, very small signal, so you can see the radio is very, very sensitive. Let's do some other calculations. My signal generator cannot generate this much, this low volume. Okay, let's draw it here. This is VP to P, and it's too low. My signal generator, the minimum I can do is 2. So if I shoot this one, how much I get? P dBm. I put into this equation, so this is 2. Log 2 is 0.3. 0.3, this is the equation. So log 2 is okay. So P2P is then it's equivalent to VPM equals to 1 milliwatts. So 1 is here, log 1 is 0. So it's neg 50 dBm. dBm. So we just say S9. How much above S9? S9 is neg 73. So it's S9 plus 23. Okay, so we get if I shoot 2 milliwatts. If I shoot 3 milliwatts, how much? If V2 3 milliwatts, so it's equal to peak value at 1.5 milliwatts. So dBm equals to 20 log 1.5 minus 50 equals 20 equals S9 plus 26. Or we know that it's yeah, it's 47 or like 47 dBm. Okay, now let's get conclusion. Let me put the paper down. Let me use red pen. Conclusion. The conclusion is that power in dBm scale equals to 20 log peak value in milliwatts minus 50, assuming R equals 50 ohm. We always use R equals 50 ohm. And the example here is if VPM P2P equals 0.14158 milliwatts, I get PdBm equals to neg 73 dBm. Oh, this is S9. Actually, let me rewrite this one. Rewrite this table. VP2PM, and this is PdBm and S meter. So it's 0.14158 milliwatts. I get neg 73 dBm, and S meter is S9. And if I shoot two P2P, I get negative 50, which is S9 plus 23. And if I send 3 P2P, I get 47, and it's S9 plus 26. Okay, the next video I'm going to show you on the radio if my equation is correct or not. So put the theory into the practice in the next video. Let's remember this table.